Alright, this video will go over the properties of functions. Alright, the first part we're going to talk about is if a function is even or odd. For even functions, if you plug in negative x into a function, you'll get the same thing out, f of x. And if you were to graph it, the graph is symmetric about the y-axis, meaning the graph is a mirror image of itself across the y-axis. And for odd functions, if you plug in f of negative x, instead of getting the same thing, you'll get the opposite thing out, negative f of x. And whenever you graph it, the graph is symmetric about the origin. Now a few examples to illustrate this for you. Now here's a three-part example. Determine whether each graph in figure 17 below is the graph of an even function and odd function, or if the graph is neither even nor odd. First with part A, if you notice right here, it's symmetric about the y-axis. Each half of the graph is a mirror image of itself across the y-axis, so that would be even. Now for part B, notice it is not a mirror image across the y-axis because each half on either side of the y-axis is not a mirror image of each other. It's not a reflection. It's also not symmetric about the origin, so this would be neither. And for part C, if you notice it's symmetric about, I guess it'd be opposite corners, like that corner and that corner are symmetric about each other. That's what we mean by symmetric about the origin. So that would be an odd function. Alright, here's another four-part example. Determine whether each of the following functions is even, odd, or neither. Then determine whether the graph is symmetric with respect to the y-axis or with respect to the origin. Or if it's neither even nor odd, it would not be symmetric with respect to either of those. Anyway, let's start with part A. Remember, you always start algebraically by plugging in f of negative x. Plugging in negative x into x. So instead of x squared, it'd be negative x squared minus 5. And this negative x squared means you'd have negative x times negative x. And then minus 5. A negative times a negative gives you a positive, so it'd be positive x squared minus 5, which is the same as f of x. So, this would be an even function. Remember, even functions are symmetric about the y-axis. So I believe this answers the question for part A. And part B, g of x is equal to x to the third minus 1. Remember, we start off by plugging in negative x. So it'd be negative x to the third minus 1, so that's equal to negative x times negative x times negative x minus 1. Negative times a negative times a negative would give you a negative x to the third minus 1. Now we know that's not even because it's not equal to the same thing that we started with. But we gotta determine if it's equal to negative g of x. Now negative g of x would be negative x to the third, negative, and then open parentheses x to the third minus 1, close parentheses, so it would be negative x to the third, and then distribute the minus, so it would be plus 1. So that's not equal to g of negative x either, so it's not even nor odd. So it's neither even nor odd. So h of x is equal to 5x to the third minus x. For part C. So, like before, we plugged in negative x. So, that's what we get after we plug in negative x. Now for this negative x to the third, that is 5 times, open parentheses, negative x times negative x times negative x, close parentheses, and then minus a negative x would turn into plus x. Now this negative times a negative times a negative would make our answer negative. So it would be negative 5x to the third plus x. Now you notice we have the same terms as in our original function, just the signs are different. So if we factor out a negative sign, this negative 5x to the third would turn into positive 5x to the third. This plus x would turn into minus x. If you notice that 5x to the third minus x is the same as h of x, but we have a minus sign in front, so that would be minus h of x. Since we plugged in negative x when we got out the opposite of what we started with, this function it's odd and it's symmetric about the origin. Alright, so for the part D, f of x is equal to the absolute value of x. Again, you have to start by plugging in negative x. So that would give you the absolute value of negative x. Now we know that anything you plug inside the absolute value is positive, so that just gives you absolute value of x again, which gives you what you started with. So this function is even, and it's symmetric about the y-axis. Alright, next property we're going to talk about is when a function is increasing and decreasing on an open interval. Remember, by an open interval, that means that it does not include the endpoints of the interval. First, to tell when a function is increasing. Function is increasing when... increasing is when, for any choice of two x values, say x1 and x2, on an open interval, let's call that open interval I, such that x1 is less than x2, we have that the y value of x1 is less than the y value of x2. And just so you know, for decreasing, in case you don't want to write that, it's the same definition. It's just that when you have when you have two x values, x1 and x2, such that x1 is less than x2, the y value of x1 is actually greater than f of x2. I figure I'd just color code it for you so you don't have to write the entire thing down again. Just so you know, when a function is constant on an open interval, it's same definition, you have two x values on that interval such that x1 is less than x2, but instead of the first y value being greater than or less than to the second one, they would be equal. Note the different colors of the words and symbols correspond to each other. But before we do some examples, I want to discuss something else. The concept of local maxima and local minima. You may also hear me use the term local extrema. They all mean the same thing. Extrema is just the general term for extreme values, both maximum and minimum together. A function has a local maximum. There's a local max at that value x equals c if there is an open interval I containing that x value c, such that for all x values in that interval, the corresponding y values are all less than or equal to the y value corresponding to x equals c. And for local minimum, the definition's the same. There's a local minimum at x equals c if there is an open interval I containing x equals c, such that for all x values in I, the corresponding y values of these x terms are greater than or equal to f of c. So the corresponding y value of that point c is lower than the corresponding y values of all other terms in the interval. That's whenever it's a local minimum. And I got an example to show you not only the local maximum minimum, but also when a function is increasing and decreasing. Here's a 4-part example. We're only going to do 11, 12, 17, and 18 in this video. So for number 11 is f increasing on the interval of -8, which would be right here, to -2. Alright, if you were to pick any two x values, say right here, from -6 to -3, you can tell that the smaller x value, f of -6, is actually less than f of -3. And that would work for, that applies to any x value on this interval, so the answer would be yes. Alright, and if it's increasing on the interval from -8 to -2, we know it's not decreasing on half the interval. And from -8, let me get another color, to -4, you notice here the y values are still increasing on that part of the interval. If the y values are still increasing over the interval, that obviously means it's not decreasing. Now for number 17, is there a local maximum at x equals 2? Alright, to tell from a graph if there's local maximum, you look to see if there are any peaks. Like here, you see how there's a peak? That means if you were to isolate a given interval, say from any interval containing this point, you see how there's a little bump right there? That means that would be a local maximum. The local maximum value would be 10. And if there's a number, like for number 18, oh yeah, first part was a yes or no question, so you could put yes. And for number 18, is there a local maximum at x equals 5? Let me switch to a different color. If you notice, there is a bump here, but that point at 5 is lower than any other point on the interval. So that would actually be no. You could go further and say it's a local minimum at 0. Because the local minimum value, when it asks for the local maximum value or y value, it's asking for the corresponding y value, which in the case of number 17 is 10, and in this case is 0. Alright. Now we're going to learn about how to determine if there are absolute extrema from a graph. It is possible to do it without a graph, but you kind of need calculus to do it, and you won't learn how to do that until next semester. Alright, here's the definition. I figured it'd be easier if I took a picture of it as opposed to writing it, so that way you could actually read it better. The definition is almost the exact same as for relative extrema. It's just that, let me highlight this part for you. Let f denote a function on some interval I. If you notice, it just says some interval. It does not say it has to be open. So, let me point this out. The difference between this and local extrema is that local extrema occurs specifically on closed intervals. Whoops, that should say local extrema occurs specifically on open intervals. So, if you have a closed interval, or if part of your interval is closed, then you will probably have either an absolute maximum or an absolute minimum. But if the interval you're looking at is completely open, you may not have absolute extrema, but you'll have local extrema. And so just keep that in mind whenever we're done with the problems. I'll show you what I'm talking about in a minute. As soon as I switch to the next slide, actually. Now for each graph in figure 23 below, find the absolute maximum and the absolute minimum of the graph if they exist. For part A, if you notice the domain is a closed interval from 0 to 5, and the highest point there is the point 36. So the absolute maximum is when x is 3, so the absolute maximum would be 6, and the absolute minimum here is when x is 0, which gives you 1. So now if we move on to part B, if you notice our interval is closed from 1 to 5. The highest point is here, so there's an absolute maximum. And that's at x equals 5, and that gives us an absolute maximum of 3. Now the absolute minimum would occur here at the lowest point, 3, 1. But if you notice, that point is not on the interval, so there would be no absolute minimum. Alright, and for part C, it is closed from 0 to 5. The absolute maximum occurs at x equals 5, and that's at 4. The absolute minimum, alright, if you notice, it's constant here from 1 to 2. That's the lowest y value, which is 1. It's 1 on the closed interval from 1 to 2, meaning every x value on that interval takes on the minimum value of 1. Alright, and for part D, if you notice, it's closed for the left endpoint, but it keeps going on and on forever from 0 to infinity. If you notice, and it's constantly increasing, so there's no, since it's constantly increasing, since the y values are increasing, there's no absolute maximum. But there is an absolute minimum. And this when it's at x equals 0 and the y value would be 0. Now for part E, notice it technically goes on from, it technically continues on and on forever from 1 to infinity. Now since it keeps increasing this way, there's no absolute maximum. And also, the lowest point here would technically be the point 3,2. But since that point is not included in the graph, there would be no absolute minimum either. Alright, next thing you're going to learn about is something called the extreme value theorem. Alright, and here's the definition. Again, I just took a picture because I figured it's easier to read it for you to read it this way. It says if f is a continuous function whose domain is a closed interval, then f has an absolute maximum and an absolute minimum on the domain. Now, the term continuous function is starred, because to have a precise definition of a continuous function, you would need calculus. However, for the sake of this video and for what you're trying to do right now, we're just going to agree that a continuous function is one whose graph has no gaps or holes and can be traced without lifting your pencil from the paper. And this kind of ties into some of the examples we were doing before, like on the previous slide, because some of those graphs had closed intervals for their domain, so you knew for a fact that they had absolute minimum and absolute maximum values. Now, if the domain is an open interval, so like if the domain is all real numbers, then depending on the particular function you're dealing with, you may have one or the other. You may have an absolute minimum or an absolute maximum, but you more than likely won't have both. Now, something else we're going to go over is called the average rate of change. Alright. This is equal to the change in y over the change in x. Something you've known about since Algebra 1. Alright. This is from x equals a to another value, x equals b. That's supposed to be a t right there. It's equal to f of b minus f of a all over b minus a. That's the average rate of change. So here's the three-part example. Find the average rate of change of 3x squared, first from 1 to 3, then from 1 to 5, and then from 1 to 7. So for part A, it'd be f of 3 minus f of 1 all over 3 minus 1. So f of 3 would be 3 times 3 squared, which would be 27. F of 1 would be 3, and then 3 minus 1 is 2. So that simplifies to 12. Part B would be f of 5 minus f of 1 all over 5 minus 1. If you plug in 5 into x, that'd be 5 squared, which is 25, times 3, which would be 75 minus f of 1, which we said was 3, and then 5 minus 1. So that's 75 minus 3 is 72, 5 minus 1 is 4, 72 minus 4 is 18. Now for part C. For part C, you'd have f of 7 minus f of 1 all over 7 minus 1. F of 7 would be 7 squared, which is 49, times 3, which is 147, minus 3 all over 7 minus 1, which is 6. 147 minus 3 is 144, divided by 6 gives you an average rate of change of 24. The secant line is the line containing 2 points, A, f of A, and B, f of B on the graph. I'm about to show you a picture so you can have an idea of what that looks like. Here's kind of what we're talking about. If you have the points A, f of A, and B, f of B, the line containing those 2 points is the secant line. And if you notice, the slope of the line containing the 2 points is just given by the y values being subtracted, divided by the difference in the x values. And if you notice, this looks like the average rate of change. This looks like the formula for the average rate of change we just went over. So, this ties into another point I'm about to make. The point I'm trying to make is that the slope of the secant line is equal to the average rate of change of a function from A to B. Alright, here's an example of finding the equation of a secant line. It's pretty much finding the equation of a line given a slope and a point that you did back in Algebra 1. It's literally the same process. So, and I'm going to show that with an example. Find the average rate of change of this function g equals 3x squared minus 2x plus 3. Find the average rate of change from negative 2 to positive 1. And then find the equation of the secant line containing those 2 points. So, let's do, for part A, it'd be the right point, which is 1 minus f of negative 2 all over 1 minus negative 2. Alright, f of 1 would be 3 times 1 squared, which is 1, minus 2 times 1, which is 2. So 3 minus 2 is 1, plus 3 is 4. Now let's plug in negative 2. Negative 2 squared is 4, times 3 is 12. Now plug in negative 2. Negative 2 times negative 2 is positive 4, so 12 plus 4, then plus 3. 12 plus 4 is 16, plus 3 is 19. So 4 minus 19, then 1 minus negative 2, which would be positive 3. So that'd be negative 15 over 3, which gives you an average rate of change of negative 5. Now in case you didn't notice, when x is 1 on that graph, y is 4. And when x is negative 2, y is 19. And the slope of the line containing those 2 points is negative 5. So you can use that slope in one of those points, it doesn't matter, and use what we call the point slope formula. Y minus y1 is equal to the slope times x minus x1. I'm going to choose the point 1, 4. You could choose the point negative 2, 19. It really does not matter one bit. But anyway, if you plug it in, it'd be y minus, if you use the first point, it'd be 4. Y minus 4 equals negative 5 times x minus 1. Alright, and you could distribute from here if you wanted to get into y equals. So it'd be negative 5x plus 5, and if you add 4, you have y equals negative 5x plus 9.